Hello everyone, welcome to the first video. Today we're just going to start with an intro to cell physiology. So let's go over some basic concepts. Cells have potentials. Now what does that mean? A potential is just essentially the difference in energy levels between two different points. And that's exactly how we can measure a potential. So if we look over here on the left and we're measuring two different points, these 2 points are within the same environment. So that's why we have a potential of 0 millivolts. But if we look over here on the right and we're measuring two different points within two different environments, such as the inside of the cell versus the outside, you can see we have a different potential. So how does the cell create this difference in energy and this potential? Well, it is established through pumps. Pumps are essentially pumping in energy, or in our case of the cell, pumping in ions that are charged, either positive or negative, and they're pumping them into this area such that there's a high concentration of them. So we create a concentration difference through these pumps. There could be a higher concentration inside of the cell versus the outside, and that is what we call a concentration gradient. But simply having a difference in energy between two environments is not enough to create and measure this potential. There are two fundamental rules to creating a potential. The first one being everything we just discussed, this difference in energy between two environments. And the second rule is that there must be some sort of connection between them, a leakiness, you could say, which connects these two environments to each other so that you can measure their difference. Think of this kind of as a waterfall. If you have a higher concentration of water, or ions for the sake of our example, at the top, we need them to flow down their concentration gradient or flow down the waterfall and get to the bottom in order to measure a difference. So we just established the idea that we have difference in ion concentrations in different environments. And in this case, we're dealing with the inside of the cell versus the outside of the cell. And that means our first condition is respected, but our second condition isn't. And that's because of this division right here. We don't have something that's linking these two for us to compare them. So let's start off with this example. We're going to deal with positive ions. You could also do it with negative, but let's just start with this example here. Now, when we do insert a channel, something that can merge these two, we have a leakiness. This positive ion is going to naturally want to go into an area where there's less of it. So it's going to go through and they're going to flow from high concentration to low concentration. Now you may think that it's just going to keep flowing through until both sides have equal concentrations. But if we move on to scenario C, there's something important that you must know. When a positive ion leaves through the channel, it leaves behind a negative charge because a positive has left the area. So when it moves through and more keep flowing through, that means we have an accumulation of negative charges on this side. And this negative charge is what's going to pull back the positive charges through. So this becomes something called our equilibrium point. Now, our equilibrium point is basically the force that we have from the concentration gradient of moving from high concentration to low is directly counteracted by the force by the electrical gradient, which is just the pull, the force that's pulling it back, the negative charge that's attracting the positive ions to come back inside. So we just established the idea of an equilibrium point with our example K+, and that was just the idea that our concentration gradient, so the ion moving from a high concentration to an area of low concentration, is directly counteracted by an electrical gradient, or the force that's pulling that ion back to its original spot. Now ions, all of these have their own equilibrium points. And there's a way to calculate their own equilibrium points, and that's through something called the Nernst equation. So if we look at this, it's a bit confusing, but R, T, and F are just constants, so we don't really need to worry about those numbers. They'll usually be provided. Something that we do need to look at is Z. Z is the charge of the ion. So if we're dealing with a positive ion, this Z is going to be a positive number. And if it's a negative ion, the Z is going to be negative. So for example, potassium, it would be +1. And chlorine would be -1. And over here, if we look, we're dealing with concentration of ion outside over concentration of the ion inside. So you would just plug in all these numbers so you can get your answer. So let's begin to talk about the resting membrane potential. Now we already went over the idea of the term potential and the two key concepts behind it. The first one being the buildup of energy, and the second one being the requirement of leakiness to connect the two environments. Now, not all ions have the same leakiness. Some are leakier than others, and the ones that are more leaky have a greater influence on the potential. So if we start looking at this cell here, and we say that it's at rest and it's not doing anything, then it's at its point, which we call the resting membrane potential. And this resting membrane potential is actually a function of all the equilibrium points of these ions involved. But not all of these ions have the same contribution to the resting membrane potential, and that's due to this leakiness that I mentioned. Now, leakiness is a layman's term. We should use a more scientific term. So we're going to start using the word permeability. We'll use those two interchangeably. So the more permeable the ion is in the cell, the greater influence it has on the resting membrane potential, since it's an average of all of them. We can also look at it mathematically using this equation here, the Goldman-Hodgkins-Katz equation. And if you look at it, it looks really familiar to the Nernst equation because it's just adapted to it. We still have our constants here, R, T, and F, and we're still using a log system. We're still looking at concentrations of an ion outside over inside. The only difference here now is that we're adding more ions to the equation, and we're also talking about the idea of permeability, or leakiness that I mentioned. Another key thing to look at here is chlorine. Chlorine in this case is inverted. We have the concentration of chlorine inside the cell over outside. And why do we do this? This is because chlorine is a negative ion, so we must flip it in order to make it fit into this equation. But you would just plug all these numbers in to get your resting membrane potential mathematically. So let's look at some scenarios to consolidate our knowledge. So the first one, in our little simulator here, we've created a scenario where the only two ions involved are sodium and potassium, and we've created it such that their equilibrium points are equal but opposing in sign. So Na is at 70 and K is at -70, and we've also played around with their leakiness or permeabilities and made them equal. Now, thinking back to everything that we've discussed, if the resting membrane potential is a function of all the equilibrium points involved and it's dependent on their leakiness, and we said that some that are more leaky have a greater effect on it, if we made everything equal, then by extension our resting membrane potential should be right in the middle. It's almost as if these cancel each other out, these numbers. So our resting membrane potential is right in the middle. Now let's look at scenario B. If we keep our equilibrium points the same, but we change their permeabilities or leakiness, let's change potassium's leakiness to something different, something higher. Notice that the resting membrane potential has veered away from this point, the 0 point, where it used to be, and it's moved down closer towards the equilibrium point of K. This is because we've stated that something that's more permeable is going to have a greater effect on the equilibrium potential. And in this case, the potassium is more permeable. Therefore, it's going to pull this closer to the equilibrium point of potassium. Okay, so back to our simulations. Let's go back to our control. So resetting everything that we just did, we take it back to all of our numbers being the same. So our permeabilities are the same again, and our equilibrium potentials are the same. Essentially, it's almost as if there's a tug of war going on. When our equilibrium points are the same, these numbers, like I said, almost cancel out. They're putting the same amount of tugging on the resting membrane potential, which is why it's right in the middle of the two. But let's change that. Let's mess around with these numbers here. So if we change the equilibrium potential of potassium, in this case, to something smaller than it was before, let's change it to -40, we notice that the resting membrane potential moves closer to the equilibrium potential of sodium. It just moved away from that steady point that we had in our control. Now, why is that? Well, if we go back to the concept that it's almost like a tug of war. The EK that we've changed, we've made the tug smaller than it was before, and we've kept this the same. So because this equilibrium potential is higher, it has a greater effect on the resting memory potential, therefore pulling it closer to it. So let's go back to our original scenario where we reset all these numbers to be the same. Let's make the permeabilities the same again and the equilibrium points of the ions involved the same again, and that'll take us back to our control where the resting memory potential is smack down in the middle. Now recall where we said the potential is affected by the permeability change of the ion. If an ion is more permeable, it has a larger effect on the resting memory potential. Well, we can also simulate that here without changing these permeabilities. Let's do it in a different way. What if we opened up a door or an ion channel of a cell, allowing large amounts of an ion to flow through it? So in this case, let's do it for potassium. Let's open our door or ion channel and allow a drastic amount of potassium ions, more than just a leak, a large amount to flow through. That's a large effect on our resting memory potential. You can also look at that mathematically if you prefer the Goldman-Hodgkin-Katz equation. The permeability values for potassium would be larger than the rest, and the other ones would be so low that they're almost negligible. Therefore, the only thing that's really changing the resting memory potential is the potassium. It has the largest effect, which is why we have a large dip, and that's why it's so close to the equilibrium point of potassium. Now, if we close it, we'll go eventually back up, open it again, and so on and so forth. And we can even flip it and say, let's open a sodium channel instead. What would happen? Well, by extension, same logic goes, it would go up just like that. It would dip upwards instead of downwards towards the equilibrium point of the sodium.